And then we head over to the next talk in the program that is given by Nicole Frommer from University of Stuttgart. I'll just switch here to the other presentation. Try it. Should work. Yeah, yes. Okay. Go ahead.
Yeah. Good morning, and also welcome from my side. Presentation is about a comparison of two concepts for energy ships using airborne wind energy. And the first question is, how do I define energy ships? So, in my situation, or in this work, the energy ships are defined as floating structures who are solely used to harvest and store energy. This gives us the opportunity for high mobility, and also we would be able to capture the higher wind speeds in the far offshore. I found multiple applications on energy ships so far, with, for example, flattener rotors, sails, parafoils. But there's nothing really existing yet, no prototypes or anything. So what I found prototype-wise was only wind-assisted propulsion, where they use basically the same systems. So the goal of this work is now to develop simplified models to evaluate the theoretical potential for the two concepts. The first concept is called pumping concept. We have here a soft kite in a pumping cycle harvesting the energy. They're all set on a ship, and then there's the consuming factor of the electric motor who propels the ship then. And the other model concept is called propulsion concept. I call it this way at least. And it's also a soft kite, and this kite in these terms pulls the ship. And the energy gets harvested by the underwater turbine here. Yeah. I start now with the modeling. So for the kite modeling of the first concept, of the pumping concept, I used a quasi-steady model by the DOF team, who are also here today a lot. And yeah, I used the predefined, there's a predefined trajectory it creates a pumping cycle, so traction, retraction, transition. And it's quasi-steady in the terms that force equilibrium is created in every position of the trajectory. Using force equilibrium includes lift, drag, and gravity. Yeah, this was what already existed. And what I added here was the ship model. So I basically started with the inclusion of the velocity triangle here. So there's a constant ship speed that we have here then. And this is predefined also, the ship speed. Yeah, and then the second implementation was the drag force. There's only drag where there's motion, so the question was where would be motion, in which directions would the ship move. First, obviously in the frontal direction. And second way, I assumed that it would move in the direction of the kite in the retraction phase. So there was a drift motion also included. And the drag coefficient of the ship is then included by independence on the wind angle here, psi. And they're also simplifying assumptions because, again, the goal is to learn about the potential. So one of the assumptions, for example, that the ship speed is way bigger than the drift speed. Then I come for the second concept, the propulsion concept. Here we have also force equilibrium. We have the propulsion force coming from the kite force directly, and on the one side, and on the other side of the equation we have the drag of the ship and the drag of the turbine on the other side. It was also necessary to include the ship speed with a velocity triangle to get a new incoming ship speed, wind speed for the kite. And the ship speed is here not predefined, and contrary to the other concept, because in this case, the ship speed is directly through the turbine going into our harvested energy, so it's part of the results. Which means that the ship speed is also dependent on all system parameters. Yeah, there are also simplifying assumptions in there. For example, that I assume that there's no vertical effect force-wise on the ship coming from the kite. Yeah. Then I came to the next question for myself. Yeah, how should we compare these two systems, because they are very different. And the obvious thing was first, okay, we compare the harvested energy, the harvested power, makes sense. But there are also other options, like the ship speed, for example. It doesn't make sense if we are faster or slower in the harbor at some point. Or the storage, do we have a minimum ship size that below it couldn't be, it's not possible to use it anymore anyways. The maneuverability also, for example, the propulsion mode is only possible to go with the wind. So we are limited there. All these points end up in the profitability, so costs here. And and it shows basically the complexity of this comparison with this task. But as a preliminary thing, I started to look only at the harvested power under the following definitions. So we evaluate over the mean power. So this means for the pumping concept that the power is averaged over all three phases. And we include the consumed energy by the additional propulsion through electricity. And for the propulsion concept, we take basically directly our results from the force equilibrium. And we look at it over the wind angle psi. So I showed it earlier, it's the angle between the ship speed and the reference wind speed. These are my definitions. And then the parameter space is also relevant for the next following results. We have as a variant parameters, the kite properties and the wind angle. And as constant parameters, we have the ship size, the ship speed, wind speed, and tether properties. Yeah, and here are my first results now. So we look now at the mean power over the angle psi, over the wind angle. And on the left-hand side, we see the pumping concept. And the right-hand side, we see the propulsion concept, both in the mean power in kilowatt. And what is now important to notice is that we have different scales here for the mean power. So radially, if you look at the left-hand side, we see it goes from -60 to 60 kilowatt, while for the propulsion concept, it goes from 0 to 6 kilowatt. We look at the different kite properties I mentioned. So these are now kites from 150 to 350 square meters. I wrote small kites in the title, but yeah, it's already quite big, I'm aware. What we can notice here now is that the pumping concept shows some negative results of -60 kilowatt. This doesn't mean that these smaller kites don't give any energy in this situation. It just means that the chip design is constant for all modelings, for all parameter combinations. So our chip basically consumes too much energy for these small kites. So it would be necessary here to adapt the ship and fit it to the kite actually. Yeah. And then we can also see here quite nicely that that there's no mean power harvested when the propulsion concept goes against the wind. So which is also what makes sense to us. We can't really get pulled by the wind if we don't have the wind in front of us or almost in front of us. Yeah. Then I dig a bit into bigger design kites. I mean, the idea was here also, we're aware that the feasibility of the technology is not there yet, but yeah, just to learn about the potential, the theoretical potential. And what we can see here now is that, again, we have here, again, our mean power over our wind angle, again, for the pumping concept and the propulsion concept. And we can see here now that the kite goes from 1,000 to 5,000 square meters, the kite. And we have, again, a different scale. So we go from 1,000 kilowatt to 5,000 kilowatt for the pumping concept, and from 0 to 1,200 kilowatt for the propulsion concept. And we can see that the pumping concept is less dependent on the wind angle now. So we basically have everywhere at least some kind of result and not negative. We can produce energy in any direction. And we can also see that the peaks changed, because beforehand the peaks were more in the upper side, in the upper half of the circle, as you can remember here, for the left-hand side. And now we're on the lower side of the circle, which also is due to our change of parameters, basically, that our parameters are fixed, and this shows the multi-dependency of the system also. In general, it's also visible that's still way higher. Even for bigger kites, the pumping concept shows higher mean power than the propulsion concept, which leads me also already to the summary. So we basically coupled ship and kite models to evaluate this pumping and propulsion system. for these energy ships. We use therefore simplified quasi-steady modeling for ship and kite as well. And the first results show that the pumping concept is less dependent on the angle of incoming wind for bigger kites, or very big kites actually. And the ship design needs to be very good fitted to the kite surface and to the kite system also. And it also shows that the pumping concept performs better for these hereby given parameters. Future work would include evaluation-wise a sensitivity study, a little hint to talk because that's my topic on talk conference. Also the evaluation metrics would make sense to look further, so maybe we should evaluate after the ship design. We have the cost model that would be necessary for the financial feasibility to evaluate after that. Modeling-wise, we definitely need to do further validations, and would be also an option to explore fixed-wing kites here, or further ship designs like catamarans. So far, there was only monohulls that we used. Yeah. Then I'm already at the end. Thanks.
Thank you. I'm glad that we are closing a gap now here, identified by Uwe that there are no ship simulation softwares. Apparently you have developed one. Uwe, you have a question.
One question. Did you take the efficiency of the generator into account?
Yes, but only with, the question was if I took the efficiency of the generator into account. I did, but only in the terms that I took some efficiency variable and as a one parameter and multiplied it. So nothing further.
Thank you.
Thank you. There is a question here.
Yeah, so I'm trying to understand your polar plots a little bit better. Can you go back to the last polar plot? So if I'm understanding correctly, an angle of 180 degrees means that the wind is coming head on with respect to the boat?
No, the different way around. I also realized that at some point that I did it in the opposite direct coordination system than the norms actually from sailing. I'm sorry for that.
Okay.
So it's directly, if we have 180 degrees, we would go against the wind then.
No worries, but then in the propulsion concept, I mean, with the propulsion concept, oh, thanks. With the propulsion concept, you need to be going in a net downwind direction, right, in order to be able to harvest usable energy for propulsion. So now I'm confused on the plot on the right. So you're saying 0 degrees is directly downwind?
Yes.
Okay. So then on the left, how are we harvesting? Is this net power here that we're talking about on the left when we're going directly upwind?
No, the thing is that the system is, the ship is now a bit too small for the system, so it's not taking really into account here. So we have basically the ship system is taken into account here, but due to the pumping cycle, it also depends on what our retraction force is, and this is here now not optimized so far. That's the thing.
Okay. Okay. Sure. Thank you.
Thank you. I think we need to continue then. So thank you again.